Hello, and thank you for giving us a chance to present our project for the Solar District Cup, the University of Nebraska LinkedIn use case. We are the University of Wisconsin-Madison team, and presenting today are, oh, it's not working for some reason. Oh, no, okay, sorry. Can I start again? Yep.
Please continue.
Mhm. Presenting today are Fahad, Sultan, and me, Mohammed. So first, let's have a quick overview of the three target areas in our design. The first and the main area is the East Campus area, where the main target was mainly maximizing the energy offset and utility savings. The second area is the agricultural area, where the main goal is to preserve the crop growth while maximizing energy production in the area. And the final area is the city campus, where the main goal was to show the university commitments to sustainability.
So, to maximize solar production in the East Campus area, our proposed design relies on rooftop PVs and carport systems. For the rooftop PVs, the array size was set to 9 panels per string, 12 strings per inverter, and these are to be ballasted on the rooftops. This mounting system ensures zero penetration and is made from recycled high molecular weight polyethylene, which should provide sufficient durability as well. This rooftop system is implemented across 17 of East Campus's buildings with a size of 3.1 megawatts. As for the carport designs, these have an average size of 42 panels and are either mono or dual pitched to maximize energy production while also providing adequate shading to the cars. The carport systems are to be mounted on a set of precast concrete and have been implemented across 6 parking lots with a system size of 1.6 megawatt. Next is the agricultural area, where the aim was to preserve crop growth while sustaining solar production in the area. And to do this, the proposed agrivoltaics design comprises conventional and reinforced regular mounted systems to preserve the various types of vegetation. The conventional ground mount system was used in areas that contained low-laying vegetation such as grass and has a total system size of 1.1 megawatts. As for the reinforced regular mount, these were used in areas where the plants were expected to be tall, such as corn, and the system is implemented with a size of 376.5 kilowatts. Next, looking at row spacing, since the plants were not expected to be high for the conventional ground mount system, the ground clearance was kept to 4.6 feet and the row spacing was set to 16.6 feet to allow the grass some access to sunlight and avoid complete shading over the plants. As for the reinforced system, the ground clearance was set to 8.2 feet to allow the crops to grow as much as possible, and the inter-row spacing was set to 28.3 feet to make it possible for large equipment to move freely in the area. And finally, to enhance the visual aesthetic of City Campus, the design approach is to use the ground-mounted systems to convey UNL's commitment to sustainability through mainly implementations of solar flowers and trees. Solar trees are to be included in the middle area of campus as a source of energy for more casual uses, such as charging smartphones or laptops. As for the solar flowers, these are a modern take on double-axis tracking that blend with the natural surroundings, and as a result, produce 40% more energy than fixed panels arrays, or fixed arrays. And for this design, we hope to adopt solar flowers in front of both UNL's Love Library and State Museum, where we anticipate the highest student traffic in the area. And finally, since City Campus operates its own distribution system, a rooftop PV is installed in the area, which spreads across the campus's 7 buildings with a total system size of 1.2 megawatts.
So after coming up with the design ideas that meet the requirements, we wanted to go back to the main idea of maximizing energy. And to do that, we needed to optimize our panel and inverter selection, in addition to our panel layout. For the module, we selected SPR X21470 since it produces relatively higher production than other possible modules, in addition to the module high efficiency compared with other modules. For the inverters, we wanted a high capacity inverter that has a good number of DC inputs and also matches the university 3-phase distribution system. Therefore, we selected Sunny Tri-Power 50 kilowatt capacity inverter. Moving on to the panel layout, we mainly focused on 2 design criteria that affect the system overall performance and cost: the tilt angle and the solar axis of the panels. To find the optimal fixed tilt angle, the relationship between energy production and angle was examined, and it can be seen that the angle of 15 produces the maximum energy compared with other angles. Thus, we decided to use it as our fixed angle. For the solar axis efficiency, the figure shows that the solar axis efficiency affects the final utility saving extracted from our financial model. The solar axis changes row spacing requirement and also the total number of panels in any building. Looking at the figure, the optimal point of solar axis efficiency that will provide the maximum utility saving was estimated to be 90%. The higher solar access efficiency fails to be an optimal point because it decreases the total number of panels, which reduces the production, while lower access efficiency panels are less effective while costing more. All in all, the system size is 7.8 megawatts, and we used more than 17,000 panels to produce more than 10 gigawatts hour. Next, it was essential for our project to have an analysis in the distribution system of the university after installing our design. And to do that, we used OpenDSS and modeled our PV system on the software. Then we identified any overvoltages in the distribution system, and the voltage values of our system will allow us to draw a conclusion about our system feasibility and change it as needed. For the modeling and simulation process, we acquired the university circuit, which was provided by the competition, and started modeling the PV system in the existing circuit. We then extracted the voltage violation exception file and plotted the grid voltage after installing the PV system and after installing the battery, which we will get into soon. So the result we got before and after installing the battery indicates that our system is under the set limits, which are 5% above and under the nominal value. Therefore, this indicates that the system doesn't experience any overvoltage and doesn't require any upgrades or smart control. And it can be seen that the results before and after are almost identical, and that's probably due to the small effect that the battery has on the distribution system, considering that the battery is only charged by the PV system inside the in the animal science building and not from the grid. The final conclusion of our analysis states that our system doesn't experience any overvoltage, and if the system had to happen in overvoltage, they can be eliminated using upgrades or smart control.
Since the project is supposed to last for decades, our goal in the development plan was to ensure that our system complied with the local codes and that it did not conflict with UNL's master plan. Regarding the local codes, we found that for our system to comply with the setback requirements, the PV panels should be placed 6 feet away from roof edge and 1.5 feet away from any obstructions. We also added a 4 feet walkway to all obstructions in the roofs used in the project to give firefighters quick access in emergency situations. And to comply with UNL's master plan, we identified all areas that have construction work planned and excluded them. As an example, you can see the area in front of the Animal Sciences building was left empty to account for the future construction work mentioned in the master plan. We followed the same approach in the Law Library and other locations around the campus. In addition, to further comply with UNL's plans, we try to avoid installing PV panels in ground areas highly susceptible to expansionary work. As for construction, we use a conservative rate of 8 man-hours per kilowatt to approximate the time needed to build the system. When we considered the system size of 7.9 megawatts, we found that 115 workers are needed in total, each working 40 hours a week to construct a system within the specified deadline of 8 months. And the overall breakdown can be seen on the screen. Moving on, the Animal Sciences building had an extra challenge where we were told to assume that the building houses and electricity dependent equipment valued at $2 million that makes up 30% of the consumption at any point in time. And so we tried to integrate a battery that could successfully support the critical loads in the building in case there was an electricity outage of 3 hours. For battery choice, we decided to go for the Power Combo C20 battery because as a lithium-ion battery, we found it to be cheaper than other alternatives. Adding to that, the Power Combo can discharge power up to a maximum of 400 kilowatts and has a capacity of 966 kilowatt hour, which was not only suitable for the application, but the extra 100 kilowatts can act as a buffer in case there was an increase in the critical loads during the project's life. As for resiliency, the C20 stores the energy in 7 separate cells, which makes it more resilient to failure than single storage unit batteries. Beside that, we found the C20 battery that can operate optimally in climate conditions like Nebraska Lincoln and have smart technology to program its charging cycles. When we tested the resiliency of the C20 battery as it works in conjunction with the Animal Sciences PV system, we found that it has a probability of surviving the outage with 95.7%, which make the battery resilient enough for our application. Moving to the financials of the battery, we found that the investors would need to pay a total of $516,000 to install the battery and maintain it throughout its life. As for UNL, re-opt showed that for the investors to achieve a return rate of 7%, UNL would need to pay $72,000 annually to get access to the battery services. And although the battery successfully lowered the building's annual utility demand cost using peak shaving, the battery was still unable to recoup all the costs incurred, and therefore resulted in a negative NPV of $281,000 for UNL. However, when considering the avoided outage cost of $2 million for the equipment, the NPV of the animal sciences building with the battery jumps up to $1.72 million, which can be further increased by roughly $34,000 if the battery is recycled at the end of its life.
So, to properly assess the financial viability of our proposed PV installation, the provided solar model template has been adapted to reflect the investor rate of return and the university savings generated by the system. The main sources of funding for the system comes from private investors, a construction loan, and a tax equity partnership flip. So the model is able to take advantage of a federal income tax credit of 26% and a five-year maker's depreciation scale, which drive the financial returns of the project. This is in addition to a power purchase agreement conducted with the off-taker, or UNL in this case, which further drives the returns of the project, and these are compared against a market estimate of 7%. And so to implement the model in the financial, or to implement the system in the financial model, 4 separate models have been developed to capture the effects of the different systems installed. The differences in these systems are reflected in the model inputs, which takes into account system size, P50 production, and construction costs. Specific system losses have been accounted for each systems in the Aurora model, which is further reflected in the P50 value or the system yield. So it was found that losses range from 7.3% in the rooftop models to 11.3% in the agrivoltaics model. As for the construction costs, these have been separately estimated for each individual system and aggregated to produce a total system cost. The main variables at play between each system include the structural, electrical components, installation labor, and overhead costs, which were found to be the lowest for the rooftop models at 29% and highest for the agrivoltaics at 40%. And using these values, the aggregate system cost was found to be $1.64 per watt, with a total construction cost of around $13 million. And after settling on the model assumptions and aggregate project inputs, a reasonable PPA was chosen to ensure that the project at least matches the desired investor rate of return of 7%. So using a PPA of 8.3 cents per kilowatt hour and a 2.5% escalator yields an investor NPV of around $10,000. And as can be seen from the cumulative cash flow plot, the federal ITC and maker's depreciation kick in over the first 5 years of the project, and then the PPA further drives the returns where a positive cash flow occurs at year 13. As for UNL's specific energy savings, the analysis has been conducted by understanding the utility structure stacked against the PPA price offered by the solar system. In terms of the utility structure, UNL operates under the secondary large light and power rate, which comprises energy, facility, demand, and customer charges. Using the customer consumption and LES rate structure, the PPA is compared against an overall utility rate of 6.9 cents per kilowatt hour with an escalation rate of 3%. And as can be seen from the plot on the right, this PPA price sets the solar production at an initially higher price than the utility, but the lower escalator applied ensures that UNL is generating some savings in the second half of the project's lifetime. So over the 20-year contractual life of the PPA, UNL is offered utility savings by the lower PPA price in the latter half of the project's life cycle. This initially higher PPA price results in negative savings over the first 8 years of the project, but is recouped through a lower escalator applied after the 9-year mark. Past this point, the university starts making a steady rise in profits, which equates to an NPV of $15,000. And although the PPA and utility charges do closely match, UNL has offered a more sustainable, resilient, and visually impressive solution to their energy needs.
So to sum it up, we believe that our team should win because our proposed system successfully meets all the conceptual design requirements set by UNL, while also producing 10.4 gigawatts of electricity annually from clean resources, which offsets 42.7% of UNL's total power consumption. Our system also generates all the electricity without causing any voltage violations and can be implemented using UNL's current distribution network with no upgrades being required. Our system is future-proof and will not create unnecessary conflicts with UNL's plans, and has a construction timeline that can easily meet UNL's deadline of 8 months. While also, by installing the system at the proposed PPA
I have
prices.
to stop you. Your time is up.